In this one, we want to find the we want to find the work done by a gas in a cylinder that expands by 5 centimeters. The radius is 2.5 centimeters, and the pressure inside is 1.5 atmospheres. And this one, we're going to have to go back to where we're looking at the different, the areas and the displacement and all that. And so, yeah, why don't you go ahead and pause the clip and try this one, and then when you're ready to check, you can hit play to continue. Okay, so we have our piston, and it can expand 0.05 meters, and so pi r squared is the area then, and so the area of that is 0.001963, and so the volume we can find by the area times the displacement there. So this will be the volume change, and this should be in meters cubed. And then when we look at the pressure, we have 1.5 atmospheres, so that'd be 151,500 pascals. And the total amount of work done then is 14.87 joules when we multiply the pressure times the change in volume there. And it would be positive work because the gas is expanding. So when we looked way back at motion graphs, so let's say we had a car that's going here at 3 meters per second, and let's say it goes for 10 seconds, right? Velocity equals displacement over time, and we have 3 meters per second. And go for 10 seconds. So let's say the car is going to go 30 meters, right, from here to wherever. So if we look at this graphically, position time, and well, not position time, velocity time. Okay, let's say it's going 3 meters per second, and it's going for 10 seconds. So that's what the graph would look like across here. Well, 3 times 10 is 30, right? So if we have velocity on the y-axis, time on the x-axis, what is actually going to give us the displacement? Well, it's the area. It's the area underneath the curve here. Will give us 30 meters. So 10 seconds, 10 is how long here, then 3 meters. So we have that. We did the same with work, right? We had a force displacement graph. And then whatever that area is, we know work equals force times displacement. We're multiplying those two things, x and y axis, multiplying those two things. This area will give us that value. Over here, velocity and time, that area will give us that value, right? So when we look at work done by a gas, we're dealing with pressure and volume, right? We're multiplying pressure times volume, and that's going to give us the work. And so, in this picture here, we have an example where we have a gas. Let's say that we have a certain gas and the pressure is just dropping, but the volume is staying the same. No work, right? But then once you're at this certain pressure and your volume expands, this area underneath here will give how much work that you have. How about here where we have a certain amount of pressure? Well, if we have a certain amount of pressure and the gas expands, we go this way. And then if the pressure stays the same and the volume, or the pressure drops but the volume stays the same, it just goes down. This entire area will give us how much work we have. And in this case here, let's say we have a certain pressure, and as the volume expands, the pressure drops a little bit. It's just, again, the area underneath would give us how much work is done. So likewise, in this picture, if we consider, a gas that, let's say we have a certain amount of pressure, it increases, decreases a little bit, all this would give us, how much work is done. Now, if though, let's say, and this would be what kind of work? Well, the volume is increasing, right? The volume is increasing, positive work. But if this gas, is compressed, right, going from a higher volume to a smaller volume, and the pressures are changing a little bit, this area here is negative work, and so the resultant, the total amount of work would actually be this inside the little oval here. And we looked at how we calculate internal energy, 3/2 nRT, and this is still going to be important as we consider our systems, because again, we have moles and they're at a certain temperature and they have a certain internal energy, and that's going to be really important here. If we look at the subtopic with thermodynamics again, this relationship with internal energy and work and heat is all going to be really important here. So internal energy is a property of a particular state of system under consideration. If two equal quantities of an ideal gas originally in different states are brought into the same state, same pressure, volume, temperature, they'll have the same internal energy regardless of the fact that they started at different states. And so that should be, pretty straightforward there. Work and heat are not state functions. They're related to the change of state in a system, but not the state itself. And so, yeah, so those are important to consider as well. Work and heat can affect the internal energy of a system, and but they are not state functions. So if we practice a derivation from energy to internal energy, we can do that, and we can derive that. And so again, as we practice that, I'll show the sequence here, and then if you want to go back and practice, or if you want to pause it right now, you can practice as well. See if you can remember this from last unit. You take the average kinetic energy, right? 3/2 NKB, KT. We know that the Boltzmann's constant's the gas constant over Na, the Avogadro's number. 3/2 N R, or 3/2 N times R over Na, replacing for K. N over Na is N, number of moles. So we have 3/2 nRT. We relate that to the ideal gas law. So we could place that in for nRT there, 2/3 U, and rearrange, then we get 3/2 pressure times volume is the internal energy. So in the steam engine, gas is expanding, it's doing work, the temperature is dropping, the pressure is dropping, the volume is increasing as it does that. So in this unit, for the most part, we're going to be dealing with a constant pressure. In real life, pressure is going to be changing. And so, you need calculus to be able to work some of those. And so we're going to get the basics here, though, with thermodynamics. So the first law of thermodynamics, we're dealing with internal energy system. And if we take our system and we put heat into our system, we know that the internal energy is going to increase. And so as that internal energy increases, that heat is causing that. So if we cool a system, the internal energy will drop. Now with work, if we take a gas, like that steam engine example, and if that gas is expanding, and it's doing work, the internal energy system is going to naturally drop. And so, but if we have a gas, like with a combustion engine, and we're compressing that gas, the internal energy will actually increase. So when we write out the first law of thermodynamics, we look at the change in internal energy of a closed system will be equal to the energy added minus the work done by the system on its surroundings. And so the change again here, change in internal energy is equal to the heat added minus the work done by the system. And that should make sense, because if you have a gas that's doing positive work, right, you're going to have, let's say it's doing positive 40 joules. When you place this in here, there's the negative already there, right? So the internal energy, and let's say there's no heat added or taken out of the system, an example, that's 0. If you did just 40 joules of work, the change in internal energy be 0 minus 40 joules of work, so you'd have negative 40 joules. And that would be the drop in internal energy. This gas would cool down, and that's what would happen, right? And so this is really the law of conservation of energy, and written in a form of thermal energy transfer. So on the IB equation sheet, you'll see this Q equals delta U plus W, which is a rearranging of the equation. If you subtract W to the other side, you get the exact same thing. So the signs are really important in this law. If heat is added to a system, Q is positive. So if you're adding heat, it'll be a positive 10 joules, 15 joules, or whatever, that you put in there. If heat is lost or a system is cooled, then we have negative Q. And so, if let's say we cool it by 20 joules, we would have negative 20 joules for that. If a system does work is positive. But if there's work done on a system, right? So the system's compressed, work is negative. And so it's important to keep these in mind as we continue here. So with this one, the system absorbs 200 joules of heat from the environment and does 100 joules of work on the environment. So it expands. What is the change in internal energy? So as you draw these out, you can just draw a simple, one like this, where you have the piston inside the cylinder, and the gas is expanding, so the piston goes upwards. And it's receiving energy, though. It's receiving 200 joules of heat. So go ahead and use the ideal gas law. See if you can, not the ideal gas law, the first law of thermodynamics, and calculate the change in internal energy for this system. All right, so we should get, there's 200 joules coming in, 200 joules, and then it's doing 100 joules of work. So in that case, it's actually the temperature, the internal energy is actually going to increase, because even though the piston is expanding and doing work, it still receives more heat coming in, and so the internal energy will increase. Let's try this one with M4. How much work does the environment do on a system if its internal energy changes from 40,000 to 45,000 joules without the addition of heat? And so go ahead and see if you can draw the situation, and then then you can see if you get that. So go ahead and pause the clip and give this a try, and then when you're ready to check, you can hit play to continue. All right, so there's negative work, and in this case here, we're doing work on a system, so the volume is getting smaller. We have the change in internal energy, the internal energy final minus internal energy initial. There's no heat adding or leaving. And so there's negative 5,000 joules of work done on the system. And that should make sense, because, the system now, it's a smaller volume, so we know it was negative work that happened here. And then, therefore, the internal energy increased as well, right? Because it went from 40,000 to 45,000 because the gas was compressed here. Let's try this one. M2a gas does work. Our gas does 450 joules of work on the environment. The internal energy only drops by 200 joules. How much heat was required for this to happen? So go ahead and pause the clip and try this one, and then when you're ready to check, you can hit play to continue. Okay. So the gas is doing work, 450 joules, and it says that the internal energy only drops by 200. So we have the internal energy dropping by 200. How much heat would that take? Well, it would take 250 joules of heat coming in. So 250 joules of heat coming in. It's doing 450 joules, so therefore it only drops by 200. So let's consider the isothermal process. This is where the temperature does not change. If we consider an isothermal process like this, where we have a gas that's expanding, like from A to B here, as the gas expands, the pressure is dropping, and that should be what happens, right? As the gas expands, the pressure will drop. Now, if it is isothermal, that means it's staying along the same temperature. And so, same thing with this one here. The pressure is dropping, the volume is increasing, but this is at a different temperature, a lower temperature. So, it's the exchange between pressure and volume. Again, these isotherms represent certain temperatures. So this is a cooler temperature, this is a warmer temperature, even the warmest temperature. So that's the initial state of the gas. Volume increases the final state of the gas. The pressure is dropping. And this is an isothermal process. So for an isothermal process to take place, we're going to have a heat reservoir to make this happen. And so, the system should remain in equilibrium, at least with this here. The heat's coming into it to make this happen, or it's being cooled if it's. All right, so in this one, we want to figure out how much heat would be needed to keep 3 moles of oxygen gas at the same temperature, held when it did 45 joules of work and expands from 0.32 to 0.45 meters cubed. And so, why don't you go ahead and pause the clip and see if you can think through that. And then when you're ready to check, you can hit play to continue. All right. So same temperature means no change in internal energy. Therefore, delta U equals Q minus W, no change in internal energy, 45 joules of positive work. So, negative the Q minus W, so positive 45 joules. We add that to the other side. So it's going to take 45 joules coming in, right? So in other words, it's going to take 45 joules of heat to come in if the gas is doing 45 joules of work, because it's going to naturally, drop in internal energy. So we would have to receive that much heat coming in to keep it the same.